number 11, where we're talking about fluctuating stresses. And by that, we're really, okay, so first let's talk about what we're covering. So section 611 talks about these fluctuating stresses, and we see some fatigue failure criteria based on them. It's usually a curve that we look at, a alternating versus mid-range curve. It's the important other graph besides the SN diagram. We're going to use this and estimate life from fatigue for some examples. Briefly talking about torsional fatigue under fluctuating stresses. Not even much, actually. And then talk about combination of loading modes, and that's probably the most important one here. All right, so the big difference between what we'd been previously doing in the last class and this is that we're going to have now a average, or let's call it a mean, a mid-range component. So it's not just going to be perfectly repeated loading. It's not going to be completely reversed. So this is sort of like the idea where we have this type of stress state. And so there's going to be a minimum and a maximum. So there's going to be an alternating component and a mid-range component. So you can kind of think where we've shifted where 0 is up high, or it could down be low in compression. And then we're going to do our alternating about that midpoint, that mean. So here's the simple equations to get the alternating and the mid-range stresses. Special cases of those where we could have the on-off loading. Sometimes we'll say that this is something that's been loaded repeatedly, which means it goes back to 0, right? So this is the on-off loading. And in that case, the alternating and the mid-range equal each other. And then you could also think now what we've previously been doing is a special case of what we're doing now, which is we have alternating and we have 0 mid-range. So we call that fully reversed or completely reversed special condition. So if we do have that condition, we can have a safety factor, similar to the safety factors we'll be using in a minute, that's entirely about fatigue. That'd be the endurance strength divided by the alternating stress. So we could say, well, that's the safety factor. And if that safety factor is greater than 1, what we're predicting is infinite life. If it's less than 1, we're predicting it will fail eventually. So here's where we're going to start thinking of this alternating versus mid-range graph that we'll be using. But check out some data points that have been plotted, and notably to the left of 0 here for the mid-range, that means that we're going to be compressive stress. We really don't have much effect. Like there isn't much difference between high and low compressive mid-range stress. And that's because if you think about, imagine the reason why we have fatigue failures that have small cracks that are opening and closing. Well, if you're in compression, the cracks won't open, right? You have to be able to have enough alternating tensile stress to be able to open those cracks. So the mid-range doesn't really have much effect, all except for a few little points. We also notice over here on the tension side that while we have a straight line that's going between essentially what is the endurance strength, SE, because we're taking a ratio of it to SE, and over here with the ultimate strength right down here. So if you go make a straight line right there, we kind of see some scattered to the outside. Then kind of describes or explains some of the curves that we're about to see, or that we use as criteria. So here's our alternating mid-range. So here are the names of these criteria before we go to a graph for them. I'm just kind of want to talk about them first. First, we have a non-fatigue constraint on this graph we're about to see. And and this graph is really very similar to the maximum shear stress theory and distortion energy graph kind of envelope idea, where if we stay inside the graph, we're fine. Outside the graph, we're predicting failure. So we start off with one that isn't actually fatigue. We call it Langer, and it's going to be a line that we draw from yield strength to yield strength. And so it's going to be a boundary. If we're inside this boundary, we're not going to yield. Outside this boundary, we predict we're going to yield. Now we have our first and our most conservative constraint, where we're going to take a look and we're going to draw a line between our endurance strength and the yield strength, and we make it a straight line. For the modified Goodman, we're about to see. I really should just show you these things besides describing them, because it's not really useful until you see the graph. For modified Goodman is the most used one we'll have, and that takes the endurance strength and goes to the ultimate strength, right? So you can making a comparison to Soderberg. They're going to yield strength. Goodman's uses ultimate strength, and I would maintain that this one makes a little bit more sense than the Soderberg. Gerber does the sort of the same thing as the Goodman, except it uses more of a parabolic. So it kind of uses more, it traces more of that curvature, which we'll see in a second. And then lastly, at least for my treatment of this, we have the ASME elliptic, which does the endurance strength to yield very much like the Soderberg, but now it does it parabolically, right? So Soderberg and Goodman are straight lines. Gerber and ASME are parabolas. There's some others in the 11th edition they start to bring up, Morrow or Moreau, whichever. Yeah, if it's not steel, this is one that they seem to use. And I won't comment on these others, except to point that they exist. Smith, Watson, Topper uses the stray life method, and Walker, which is a more generalized version of the one above. All right, so here are these curves we talked about, and now we can see them. I don't know why I waited to do this. I should have put this one up first. All right, so here's your Langer. As I said, we attach the yield strength to yield strength, and I kind of think of this when we go to the Goodman, and we call it the modified Goodman, as being the thing that we're doing to modify it, right? Because over onto this side over here, anything over to this side, what we're really saying is that, well, it's going to yield, but then we start to talk about the fatigue. But maybe if it yields, it's already failed, right? So that's before we even have fatigue being addressed in there. And so I kind of think of the Goodman up to that point right there as being based on the fatigue line, and then we're going to say, well, okay, now after this little cross, we're going to judge it by the yield strength. Anyway, so there's the Langer line. So here's the Soderberg, and you can kind of see this fence. It's the most conservative there because it's the lowest down. So of course, once again, if you have a point as they're plotting right here in the chord, this is easily be sigma A and sigma M, and you're plotting this point, you can see that with this load line passing through here, that you are outside the boundary of Soderberg. So for that little point A that they're showing on here, as an example, that would not pass Soderberg. You'd have Soderberg that was a safety factor less than 1. Here's the modified Goodman, and I meant to put Goodman inside there. Let me fix him. Modified. I think it needs a hyphen in there. Goodman. Goodman. I knew there was something in here I didn't like. Okay. So the modified Goodman here in green, and their load line, they happen to have put in this point right here, SA and SM, is passing and touching on the Goodman line. So that would be a safety factor of 1 for Goodman, as what they've drawn here. And then including in here is the curvature one, which is the endurance strength to ultimate strength, the Gerber. Right there, you can see the Gerber line left, right? And you can see that it is pretty much following the endpoints of the Goodman, but it is following a curve, and you could rationalize why is it making a curve. Well, sorry, I overshot here because of this right here, right? So it's following those points a little bit more closely. Boom, boom, boom. Okay, and then lastly we have the ASME elliptic right into there. In the 10th and earlier editions, the equations for the safety factors associated, they're in these tables. For some reason, they're buried in here. But here's the one the first one that I'm pointing out in 6.6 is for the Goodman safety factor. You're taking 1 over the addition of these ratios. And you can think of these as being apples to apples because we have alternating and then mid-range. So this is a fatigue is alternating stress, and this is a fatigue strength, endurance strength. So we're taking the ratio of those, and we're adding to it the ratio of these constant stresses. So the mid-range stress is a constant stress, and the ultimate strength is based on constant stress. So it's apples and apples on comparison. So you're taking these ratios and you're taking one over them. So you end up getting like the contribution of each one to them. And but graphically it comes out as a line like right here. And if you plotted a point and then you draw your load line through there and you took the ratio of the lengths, you'd be able to see that you would get the same factor. Okay, so 6, 7, they do Gerber next. So here's where that safety factor is. And once again, this is where you would find it in the 10th edition. I think it's called out separately as an equation in the 11th edition. So more complicated, a little weirder. And then in table 6.8 here is for the ASME elliptic. And I think the Soderberg is somewhere listed separately in the 10th edition, but it's also listed separately in the 11th edition. So here are the safety factors. First, the Langer. And what you're really just doing is taking the yield strength and dividing it by the maximum stress. Right? If you go back to the curves in the very beginning, where you look at the alternating and the mid-range, if you add them together, they should equal what the maximum stress is. So it makes sense. So this is like a first time. It's not a fatigue safety factor. It's just a first time that you put a load onto the thing, the maximum stress that you put in. We'll see that when we do combination loadings, this could be kind of a little bit messed up because we would get a different number if you just did this. After you made these into von Mises stresses separately and then you added them together, you would get a much larger stress, not a much larger, but a larger stress than if you just found what the maximum von Mises was. Soderberg, not written here yet, but it is still that apples to apples type of thing where you're comparing, here's the alternating and the endurance strength, and now you're taking the mid-range and taking the yield strength instead, right? The Goodman, I think, is makes more sense in the sense that it makes more sense in the sense that than Soderberg, because the failure as fatigue is the part breaking apart into things. So when it comes to the static element of it, the mid-range element, we could make that same comparison of the thing coming apart into pieces, as opposed to making it compared to whether it just bent and won't come back into its original position when it comes to yield. So that's why I would maintain the Goodman has a little bit more sensible comparison, apples to apples wise. Then we've already put in the Gerber. It's a longer equation right there, and we're basically just curve fitting. And then an easier but same concept for the ASME elliptic. And I don't know why they don't just put the ultimate, just put the ultimate in there. I'm not sure what that would necessarily look like and why that would cause trouble, but the Gerber is a little bit more complicated than the ASME elliptic. Here's some rationalization of why we're still doing this, even though years have shown that this is not a really predictive type of thing. It's conservative. That's good news, right? And it's a stepping stone to understanding it, is one of the rites of passage. And this is how engineers work, talk with each other and exchange ideas. So if you needed something more complicated than the approach that we're taking, you would still be using some of this in their discussion. So it's worth covering, even though we've established that this goes all back to 1890 in this mindset. And Soderberg was 1930, so it was more, less. This one was over 100 years, but this was even a little bit less than 100 years in the making. So anyway, we're using this. So what does this mean if you have a safety factor below 1, where we've kind of already mentioned that that means that the thing will fail. That means it's not down here in that region. It means it's higher up. So somewhere in here. So then as soon as it fails, as soon as it has a safety factor below 1, it'd be a good thing to now predict how long it's going to live. So what we need to do is we need to find an equivalent completely reversed stress so we can enter it into what we did in the last class, in class 10, to be able to predict failure. All right, so here's the method I prefer, right? Well, we're just going to stick with Goodman, even though you could use other methods and do pretty much the same type of thing, right? But we're going to stick with Goodman. What we can do is we can plot we have an equation called right here. It's equation 659 in the 11th edition. It's hidden in the example 612 where they demonstrate doing this. But what you're basically doing is once you've established that you have a Goodman that's below 1, now let's go backwards and see, well, what endurance strength would it take for this thing to pass? Maybe is much what you might want to say. So we're gonna make our own curve. We're gonna find the intersection, right? So we're gonna note the graphical method here. So if we draw, okay, so if we plot our point, so I have these kind of backwards here. Let me fix that here. 4 needs to be higher than the straight line, right? Right there. Let's see. Note the graph. I don't even like to note the graphical thing. I don't even know why we have that in there. But okay. So we plot our point and we can draw a straight line through it. And that's basically what that equation does. We get that value right here by plotting this out. And so if you take a little comparison to what our safety factor equation looked like, we set our safety factor to 1, and then we kind of solved for the endurance strength. This is what we would end up getting. So here's an example. Let me see how much time I've passed through here. 17 minutes. Let's stop it and go through the